All right, another Physics Teachers Are Awesome physics reaction video. Today I did a search for quantum tunneling. So here's what we got. Let's go.
Tunneling through a potential energy barrier. Now we have a particle that is incident on a barrier from the left-hand side, which is called region 1, where the particle is free to move in a potential well with a finite barrier. Now, as we have seen in the previous problem, when the particle is incident on a finite barrier, its wave function decays exponentially inside the barrier. So those were the solutions we had in regions 1 and 3. So with that, we have...
Just wanted to comment a little bit on the zooming that's happening. I think it's super useful to be able to, number one, have all of your old notes there. That's really cool. To be able to go back and say, hey, we used to do this. And then to be able to really zoom in to be able to see the details of the image. One of the things I'm going to watch for, because I've put a lot of thought into quantum tunneling. In fact, I have this whole blog post on a whole new way of calculating it that's just faster than the standard ways. So I've really put a lot of thought into this, and there's a lot of features of it that I think are really difficult for students. So number one, this arrow here is indicating that the particle is coming in from the left-hand side. But that doesn't mean that this wave is washing in, right? So it's tough, right? Because this is just the real part. And so you'd always also have to plot the imaginary part. Then it shows this exponential decay. And so what we really want to understand is what's happening sort of over time. And to model things over time, you don't just do a single wave function, a single wavelength. You have to have like a packet. And that just gets really nasty. So I have always really appreciated these things. And of course, by doing a barrier that's perfectly flat over the top, so you really only have these three regions is the most straightforward way to do it, and still leads to the just amazing results that you actually get anything over here, right? Because if this is your energy, and this is your potential energy in classical mechanics, you're not going to get past it. And yet suddenly we see some things over here. I'll also comment on just the incredible mix of ideas here. So we've got a plot of the wave function, so it's like the square root of probability, the units of that. And we have a plot of energy on top of each other. And so both of them share the same x-axis, but they have incredibly different units of the y-axis.
This sinusoidal wave function decaying exponentially inside this barrier. Now, if this barrier has a width L, it's going to be called a square barrier, and the other side I'm going to call region 3. If this exponential decay does not go to 0 when the particle...
By the way, I love the highlighted mouse. I've talked before about how not all screen recording software lets you highlight the mouse. You literally have to draw and leave behind digital ink, which messes everything up. But I think that this highlighted mouse works really well. This looks super familiar to me, these pens up top, but I can't remember what software this is.
Enters the barrier or exits the barrier, then it can make it to the other side, and it will have a solution for its wave function on region 3. Now, here I'm assuming that the energy of the particle that is incident on the square barrier from the left-hand side is less than the potential energy U. Okay, so what happens classically? Classically, regions 2 and 3, these two regions are forbidden. Why are they forbidden? Let's see. The energy of the particle E is its potential energy plus the kinetic energy. Now, if the energy minus the potential energy is less than 0, that is, the energy of the particle is less than the height of this barrier, that would imply that the kinetic energy of the particle would be negative.
Right.
Now, that doesn't make any sense, so this particle cannot go into the barrier, so there won't be any possibility of finding the particle in region 2 or region 3. However, quantum mechanically, this is possible. According to the uncertainty principle, the particle can penetrate the barrier for a short time interval.
I really like that connection, right? So to say that there is a discrepancy in the energy, right? So this is not allowed. Just doesn't make any sense. But what if you actually didn't know the energy that accurately, right? So you had a delta E that leads to a delta T discrepancy, which gives it just enough time to make it through. So I'm trying to remember. I did this calculation once before. I believe that if you calculate the time it takes to go through, that leads to enough uncertainty of energy that you don't really have this going on. Now, the question is, what happens if you go and put a detector in there? Would you actually detect something, and what the heck are you detecting? So that's complicated.
Heisenberg's uncertainty principle tells us that delta E times delta T is greater or equal to h bar over 2. Okay, so that's just the detail. Basically, we're saying that quantum mechanically it's possible that the particle can penetrate this square barrier. The movement of the particle to the far side of the barrier, the fact that this particle can enter the barrier and go to the other side of the barrier is called tunneling. Alright? So the probability of tunneling can be described by a transmission coefficient T and a reflection coefficient R. So the probability of transmission to the other side is T. The probability of reflection back to the first region is R. T plus R obviously is equal to 1. The particle will either be transmitted to the right hand side or it will be reflected and remain in the region 1. What is the probability of the transmission of this particle? Well, that is given by the square of the wave function in region number 2. So in region number 2, remember that inside the barrier, our solutions are exponentially decaying. Therefore, the probability of making it to the other side would be equal to e to the minus kx square, or it will be proportional to e to the minus kx square, while x is equal to the width of this barrier L, so it will be e to the minus 2kL. So the transmission coefficient will be proportional to e to the minus 2kL, which is related to the square of the wave function solution in region 2 for x equals L.
I really like that. I really like pointing out where the exponential comes from, why the negative sign is there, why the L is there. The K, is a little more subtle, but they have recently done that problem with the finite square well. And then I loved that just the very last thing he said that explains why there's a 2 there. So every piece of this got a little bit of attention. It's exponential. It's a decaying exponential. It has to do with how far you have to penetrate through that. It has to do with the basically K tells you how much there's an energy difference, and then the 2 comes from the squaring. That was really cool.
Making it to the to region 3. Now, what is K here? K that appears here. K is the wave function. K is the wave vector K, and which has a magnitude square root 2m u minus e over h bar square. Remember that these are bound solutions, so u is greater than e, so this k is a real number. Therefore, this is going to be an exponential decay with barrier thickness. So you can see that as L increases, the probability of getting tunneling to the other side decays exponentially. Okay, so we talked about the tunneling process, tunneling through a potential energy barrier. We recall the solutions in regions where we have zero potential energy to be sinusoidal solutions. The solutions should match at the boundaries, and the derivative must be continuous as well. And these requirements told us that in region 2 we should have an exponential decay of the wave function when we go to this boundary between region 1 and 2, approaching from the left hand side. Now, if this barrier has a width L, it's a square barrier, and if the energy of the particle is less than the potential energy, classically we see that the energy of the particle is potential plus kinetic. E minus u less than 0 implies kinetic energy less than 0. So the particle cannot exist in regions 2 and 3 classically. Quantum mechanically it can, according to the uncertainty principle, for a short time interval.
I'm just going to stop there. This is really, really great. I thought that the setup was fantastic. By the way, the technology being used is really cool with the zooming. I really loved how he carefully laid out what's going on in all three regions, and he's definitely laid down the principles that are going to be needed to figure this stuff out, right? So he said that the wave function and its slope have to be continuous here and here. Well, so typically what we have is a right and a left traveling wave here, a right traveling wave there. So that's 1, 2, 3 things we have to figure out. And then in here you actually have exponential, excuse me, and exponential in both directions. And so you actually have a couple of things to solve in there too. But the boundary conditions are what sort of does it for us, and all we ever actually care about is the ratio of the amplitude here to the amplitude there, because we don't know how many electrons we're going to fire at it. And so it's really just the ratio that matters. And so that sort of then leads to just enough information that we can calculate this, which is actually really, really cool. So I thought this was great. And so I think that I think you can tell that moving on from here, there's some subtle calculations that need to get done. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.